Hello everyone. Today we will continue to look at the content of HCI-Storage that we introduced before. Address mapping management and the data relationship of flash memory chips. Next, we will specifically introduce the HCIE flash translation layer we mentioned in the last class, which plays a major role in our solid-state drives. So first of all, because of the rapid development of storage, right? Solid-state drives are now being used more and more. Its main advantage is high-speed reading and writing, which is its primary mainstream advantage. And in our solid-state drives, the flash translation layer actually plays the most crucial role in this aspect. So here, first let's take a look at its basic concept. The flash translation layer is actually like a bridge, connecting our operating system to the logical address recognized by it, and to the physical address of our flash memory. Why is such a bridge needed? Actually, this starts with the characteristics of our flash memory. Flash memory, in fact, compared to traditional media, has different read and write characteristics, right? As we mentioned earlier, it cannot perform overwrite operations like traditional mechanical hard drives. It can only erase before writing. This results in the logical address and the physical address of the flash memory not being able to correspond directly, so a bridge is needed to connect the physical and logical addresses. It allows us to find the exact location where our data is stored, which is a very important point. No matter how fast you are, if you can't find the data, right? If you can't find the data after writing it, that's definitely not okay, right? Then no matter how fast you are, it's useless. So in this regard, first of all, let's take a look at the flash translation layer. The most important role. Here is our main controller. The main controller, here, first of all, it acts like a commander, coordinating the work of all the internal components within our solid-state drive. Then here, we have an FTL mapping table that plays a crucial role. Its storage location has multiple options. It can be stored in our internal static random access memory, or it can be stored in dynamic magnetic random access memory, or it can be placed in external flash memory chips. Basically, it can be placed anywhere. Placing it anywhere doesn't have much impact. The main function, right? It is to map our physical addresses and logical addresses according to the address in our mapping table. That's its role. Now, the interaction between our operating system and flash memory is like this. First, the size of the sectors in our operating system. We mentioned earlier that it's 512B, and the file system also reads and writes in units of 512B. This is like borrowing books in a library where you have to borrow at least one book each time, right? You can't borrow just a part of a book. This one book. It's equivalent to our operating system issuing a read or write request. And the main thing specified in this read or write request is our logical address, which is a sector address in units of 512B. For example, like sector 0, sector 1, these kinds of sector positions. After specifying the sector, our flash translation layer starts to perform the mapping function. The main controller will map according to the address in our mapping table. Suppose let's assume the operating system requests, for example, data from sector 1. The main controller will then look in the mapping table, right in our mapping table, to find the physical address corresponding to sector 1. It's like when you go to a library to find a book, right? What do you need? You need to look at the book index. It's the same principle. So how is the data specifically stored at the physical address of the flash memory? Well, it's actually stored according to the arrangement in the mapping table. Each logical sector recognized by the operating system will have a corresponding storage location in the physical address of our flash memory. This relationship is akin to a precise coordinate transformation system, ensuring that our data can be stored and retrieved accurately. For example, data from mountainous forests might be stored at a specific physical location in our flash memory. This location will be recorded in the mapping table, and it could be placed anywhere. Once it's placed, it will be noted down, making it easier for subsequent retrieval. Making subsequent retrieval easier. This flash translation layer actually plays a crucial role in the performance and reliability of our solid-state drives. What does it mean to erase an entire block first? It means clearing out the entire block completely, and then writing to it. This is one reason why the write speed of flash memory is relatively slow. The write speed, relatively speaking, is because it doesn't write directly or overwrite directly. Instead, it first erases, clears the original data, and then writes new data. This is our block. Going up one level. 1478 blocks can form a plane. A complete flash chip is mainly composed of two areas. One area stores blocks with odd numbers, and the other stores blocks with even numbers. In the end, there are two. Pay attention, there are two. The planes are multiplied by something to form a whole. One records odd numbers, and the other records even numbers divided into two parts. These two planes can operate in parallel, and this parallel operation can improve the read and write performance of our flash memory. It's like having two factories, two production lines working simultaneously, so naturally the efficiency will increase. This is one of the main function of a plane. In practical applications, when our solid-state drive reads data, the two planes can simultaneously read data from different blocks, effectively doubling the data speed. The data speed is directly doubled. This is the composition of one of our blocks. In addition to this, we also mentioned earlier the concept of ECC, which is an error correction code. This error correction code is mainly used in flash memory storage. It mainly serves the purpose of addressing the issue. That as the number of write and erase cycles increases, the storage performance of our cells will degrade, and the probability of errors will increase. At this point, the error correction code becomes very important, as it can effectively reduce the occurrence of errors. This is the main use of our error correction code. The main use. From the perspective of storage device performance, the data relationship of our flash memory chips can actually affect the overall performance of our devices. For example, the design of our configuration and block size will affect our read and write speeds as well as storage efficiency. The smaller the configuration, the higher our read performance will be. However, it will increase the number of write operations. So what if the block size is larger? Well, this can improve write efficiency. However, when modifying small data, it may cause unnecessary erase operations, which in turn can affect the lifespan of our flash memory. Therefore, in the design and manufacturing process of flash memory chips, various factors need to be considered, such as optimizing configuration parameters like block size, to achieve an optimal balance between performance and lifespan. In actual flash memory applications, wear leveling technology comes into play. This is because the number of erase cycles for our flash memory is limited. Why? For instance, if your flash memory reaches the maximum number of erase cycles, then your solid-state drive will frequently encounter issues such as the errors we mentioned earlier during the transmission process. In such cases, if the errors continue to increase, this actually becomes an irreversible problem. Even with error checking, it can't be completely verified, because if there are too many errors, the overall effect is already equivalent to reaching the end of its lifespan. So everyone should definitely pay attention to this. The lifespan of a solid-state drive mainly depends on the number of erase cycles. For instance, if you've used it for a long time, but don't frequently erase data, then in such cases, the lifespan will actually be longer. But if you frequently erase data, then the lifespan will actually be shorter than expected. This is an issue of wear and tear, shall we? A problem of wear and tear. Well, wear leveling technology actually uses algorithms to evenly distribute the erase cycles across all the blocks. This way, each block shares the erase cycles equally, which extends the overall lifespan. It helps prevent situations where only one block fails, thus minimizing such occurrences. It's like a car, right? You can't just use one tire if one tire wears out, right? The other tires can't be used together either, and you need to replace a tire. It's the same principle here. This is the basic relationship of our flash memory chip data. If you want to learn Washington technology or obtain the Washington question bank, please send me a private message. I can also leave more comments below the video for technical exchanges. Alright, let's stop here for today.